Welcome to PCB Chat. I'm Andy Shaughnessy, content architect with the Printed Circuit Engineering Association. Joining me today is CJ Clark, co-founder of Tomachie, an AI-driven schematic analysis platform, and also the name of the company. How are you doing, CJ?
I'm great. Thanks, Andy. Thanks for having me on. I really appreciate it.
Glad to talk to you. CJ, why don't we start off? Why don't you give us a little background about yourself?
Sure. I started out as the CEO of Intellitech. That's how Tomachie, I guess, got funded and started. Intellitech has been involved in creating IEEE standards like 1149.1. So I've written 2 or 3 standards, and Tomachie kind of sprung out of our need for dealing with data for test. So for about 3 decades now, we've been trying to get netless and EDIF formats and so forth, CAD data into the test flow. And it's always lacking having the full design information that you need. So we started looking at that problem almost 2 years ago now, and Tomachie sprung out of it.
But there's a lot of confusion about what AI can and can't do in PCB design, PCB analysis, PCB manufacturing. Tell us your thoughts on this, CJ.
Sure. Let me address it at kind of the high level first. Tomachie is a platform for looking at a design, reading the native CAD formats, doing an analysis without AI, right? Doing an analysis for many different things, including boundary scan and those types of things, automatic inspection and AXI, automatic X-ray. And then it adds AI on the top. So what I want to be clear to your audience is that we're not competing against Altium or OrCAD or KiCad and reinventing that wheel. Our platform is to use the tools that are already there, the data from the tools that are already present. So it's much different than some of the other solutions that are out there, which are brand new CAD systems that allegedly give you AI assistance in designing or AI assistance in doing printed circuit board layout. Now, from our perspective, layout and schematic capture are 2 things, yes, that can be automated. They're both very difficult, especially layout. We didn't try to capture that because it's just too big a job for us to get to. And the same, schematic capture itself, automating that requires a certain amount of knowledge. What we're doing is putting AI where we think it's most powerful right now, and that is to analyze a design. Not in the sense that some of the things that you see out there do, like look for a diode being backwards. That's a little use for most designers who kind of know what they're doing, that they're not putting in Zehners in incorrectly. But what we are doing is doing this analysis to figure out where do I have coverage through optical inspection? What are the inspection types that are available? And where do I get coverage from in-circuit test? And where do I get coverage from boundary scan? And then from that analysis, figuring out what additional nets and targets would give me the most fault coverage. And this is done at the schematic phase, long before layout, so we can figure out what the fault coverage will be before we get to layout. This process currently is done by guessing. Where should I put the test points? Well, over here looks good, and I should go here, but it's not being done through measurement. And that's what Tomachie's doing. It's not only looking at where the best nets are to give you the maximum fault coverage for the number of test points you can put in, but it's then inserting those test points. And all of this is done actually without AI. This is all done through the Tomachie platform. It inserts the test points. It nudges the reference designators. It's quite impressive to see how it can fit in test points into various parts of the design. Just doing it and then writing out your native CAD files back. So if you're an Altium user, you're going to get test points put into a modified design, which it then sends you an email, and you can then go and download that modified design with the test points in it.
Right.
Then what we're doing with the AI is, okay, now let's look at things like EMC compliance, ESD protection. Let's look at the power overview, and can we document? So we're focusing AI towards things that we know it can do. As a designer, I've done a couple of print circuit boards myself in my lifetime, most recently KiCad in the last couple of years. The documentation phase is something that takes a lot of time to write out, and a lot of stakeholders don't know how to read a schematic, or don't have the time to read a schematic. And there's a lot of work that you have to do. When you have a schematic, you then have to pull out the data sheets to refer to the components that are present to figure if things are correct or not. Right. And what we do with the AI is to analyze the design. So we look at the design overview and document the design through AI, so the designer himself doesn't have to do that. So you can get 3 or 4 pages of explanation as to what this design does, that you don't have to, all written in prose, that you don't have to write yourself as a designer. So that alone is a huge savings. But then it does checks. When you get to the power overview section, it goes through and looks at the power. Do you have the feedback resistors, for instance, going back to the regulator? Are those correct? It looks at, and then when you get to ESD, it looks at, do you have the ESD diodes? And then it looks at the industry that you're in. So it will look, oh, this is a medical board, this is a automotive type board, and it will then apply the right standards. So if you have an automotive board and you have to meet an ISO standard, which you do, then it will look for that compliance. And if you have a TVS diodes on your signals, do you have the proper EMC check, EMC protection that's necessary? Then it looks at that, and then and across the different standards that are present.
And now a word from our sponsor. Join the electronics design and manufacturing industry at PCB West 2026, coming September 29th to October 2nd to the Santa Clara, California Convention Center. Sponsored by the Printed Circuit Engineering Association, PCB West is the place thousands of designers, engineers, fabricators, and assemblers of printed circuit boards go for learning the latest in components, ECAD, and manufacturing processes. From drones to automated vehicles to wearables, there's something for everyone involved in the electronics supply chain. This is one show you cannot afford to miss. Registration for the conference and exhibition is now open. Be sure to book your spot. For more information about PCB West, visit pcbwest.com. Brought to you by PCEA, Engineering Tomorrow's Electronics.
Well, CJ, there's been some reluctance on behalf of designers as far as AI goes. What is causing this, and what can be done to sway? They are sort of coming over slowly.
Sure. The designers are risk adverse, and they need compelling reasons to move to a new technology. And I think what's been shown so far hasn't been commercial level tools. So there's a YouTube video with a very good designer, but he's made a interface into Fusion and did some neat things with it, and he had up to 100 checks that in the design. And then there's a kid over in New York who has something which will check to see if your diode is in backwards or not.
Hmm.
And I think there's another one up on GitHub. So there's been kind of designer to designer, look at what I've done, isn't this neat type of thing,
Right.
but nothing that's at a commercial level where the project manager or the stakeholders could embrace it.
Hmm.
Right. So you don't want to be you don't want to be fiddling in your cubicle with a toy, right, when you should be working on the design. So people want something that's very robust. So we come from our background with Intellitech. We have lots of designs that we have been able to validate and we use. We know what an industrial design. Some of the designs we have are like 100 pages long. And so with that means that you have to understand how to scale, how to work with the particular industry things like in a real industrial environment where you also have production test. So those things have to be in place. So I think it's the approach. So the AI, what people have seen and what's getting the most amount of attention has been more, isn't this neat, as opposed to here's a commercial tool. So
Hmm.
Tomachie, what it will do for you, by the way, is it's a great tool for contractors or people looking at contractors because you can measure the design. Tomachie will give you a report besides the AI part, but it also gives you a report and a score of how ready your design is for layout.
Hmm.
So again, we're looking at the schematic phase of it and then scoring it, saying, well, here are the things that you could do to get a better score. And we don't have any scores that are above, I think the highest score we have is like 86 right now.
Hmm.
So there is some work that every design that we see needs to have in order to be ready for layout. And then you can also think of it as also be ready for AI. So there are things that people have done in the past that have been kind of ad hoc, and AI doesn't work well with that, right? So if you put a note on your schematic and you say, oh, well, these two lines are differentials and should be 100 ohms, and it's just a text layer note, right? Not setting a property like you can in Altium. You can set a property to say these are differentials, and you can set a property to say these are in a class of 100 ohms. But just telling, in plain text, then you relied on the layout engineer to read that PDF and then take the right appropriate action as a human.
Right.
And that doesn't work so well when you get into even Altium has, automated managers or wizards that help you. But when you start moving your information into an AI tool, it needs to have the data specifically done in a certain way. IPC footprint, right?
Hmm.
So IPC 7351B is a standard for how you name a footprint and then also how you call out that footprint. And if you don't do that and you're just doing a design at home as a hobbyist or a student, then it probably doesn't matter too much. But if you don't use the IPC name, then downstream tools don't know how to use it, whether it's AI or
Hmm.
it's a pick and place machine or it's optical inspection, right?
Right.
So we're doing those checks to make sure you're starting to move your designs towards having them being more robust, or what we say hardened. The design is hardened, ready for layout because all these checks have been done and you've updated it such that it works well with AI and it works with all the downstream tools. And then that lowers your friction. So if you're a designer, why should I do this? Well, it gives you documentation. It pleases your stakeholders. It lowers the friction for people downstream that want to have test capability. So it's helping the designer get to those goals, and then also helping the company get this kind of information earlier on rather than waiting until layout to start thinking about test points. We do it much earlier in the design cycle.
And I think it's really nice that you, like for instance, with the generative DFT, where it suggests these test points, where it places them into the design, it places them right into the Altium or the KiCad file.
So in the old days, right, we would just generate a report to say, oh, these nets we used to sell a tool at Intellitech, these nets are the ones that you don't need test points on, right? But it's like a manual thing. And what we've done now is automate it. So it's another thing to look at. The tools that are taking pads output or wireless, the type of thing you'd pass to an in-circuit tester, those aren't going to work well because you can't insert test points, right? It's all passive, looking at an output out of the CAD rather than writing to the native CAD files. And so inserting is really where the time saving is. We're not just telling you where those test points should go, but we actually put them in there for you. And then there's some other fix-ups we'll be doing that haven't actually been released yet. But for instance, we look at on HSSI, so your high-speed serial interfaces, you can have your impedance, even if you put down impedance blankets and so forth. But if you put a component on there, you might end up having an impedance discontinuity, right? Or what we call an impedance gap, where there was a segment of that path from the chip all the way to the connector. Someplace along that path, you forgot to say it should be 100 ohms, right? Well, a good layout engineer would know what to do there. But again, if you're going into automation, then you want to make sure that it's all explicitly defined. So we'll go in, we tag it right now, but our next step will be to actually specify and add into the design that, that's also 100 ohms, controlled impedance. So if you're going to take this design and you're going to pass it off, you really want to do a lot of things with it. So the guys that are offering, well, I'll do this on your design and give you a little bit of feedback, but then you still have to go off and do your boundary scan portion, right? So as a separate thing. And what we're doing is saying, look, we want to do this all in one pass because we get some advantages of it being integrated together. And that is that we get the information that we can pass into AI such that AI can do a good job. AI is, it's smart and it's dumb at the same time, right? If you give it too much stuff, it gets confused. There is just no way you can take, on any AI platform, you cannot take, I was going to say 100-page design. You can't even take a 20-page design and pass it to an AI system and have it give you reliable answers. And if you took that PDF and you said, well, I'm going to write it as a net list and pass it to AI, it still is going to be confused. And when you have BGAs, that are 1,500 ball BGAs, you have a huge amount of decoupling caps. All of that overwhelms the AI and it can't figure things out. So what Tomachie does really well, again, because our background is from Intellitech and working with CAD data for decades now, what we do really well is compress the data. We figure out what are the important things that AI needs to know in order to do a good job. And we're getting that information because we're processing your design first and figuring things out, like where do you have an impedance problem, or we're extracting the EMC information. If you put an EMC barrier note, in your page, we collect that and look at it and say, okay, this is something that we have to take into account. So processing the information all up front is key to scalability for large designs, but it's also key to accuracy and preventing AI from hallucinating.
Hallucinating AI.
Yeah, well, you get it all the time. We every day we see it every day. So as we go and debug and create the product for our customers, we see it every day. It goes off and it says something that you just don't expect it to do, and then you have to research and look to find out why it's doing that, and then we go and give it additional information. I don't want to explain exactly how we do everything, but a feedback. So guys that are doing power supply designs and they use regulators, they know that they usually have to do a voltage divider to pass voltage to the feedback of the regulator. And you can't give AI a list, say, here, go figure this out. It can't figure out all those things. So we tell it. We tell it explicitly what things it needs to be doing, And so then it helps it. So it needs all this kind of help. And then that's what we do really well, is really curating the data, right, by analyzing it first and then having AI do something with the data. I probably said more than I should, but
No, that's good. I like this layout readiness score that's just 0 to 100, that it takes out this interpersonal tension where you have a junior engineer not wanting to question the senior engineer, and the newbie doesn't want to look like a fool. Comes right out. Oh, this passed it. You take out a lot of
does that make sense? So like nobody wants to, other than me, nobody wants to be pedantic. So I've worked in standards. So I have several decades of chair as IEEE 1149.1 that people, your audience would know as JTAG, and then 1149.10. So I'm used to being very pedantic about, definitions and how the wording should be done in a standard. And so we take that same approach here. And normally, that junior engineer doesn't want to say, well, your value, you stuck the percentage. We saw that just recently, where the resistor values also had a tolerance stuck on them. So it was, 10K plus or minus 5%. And that causes problems downstream because the tools aren't used to consuming that information. So the junior engineer is not going to speak up at the meeting and say, oh, you've got 5% in there, because it seems like you're being nitpicky. And so we let the tool be the nitpicker, and that removes any of the social problems that might be present, right, when it goes to doing the design reviews. And it gives you, a score, and it gives you a list. Not just a list, but a link to where to learn about it. It gives you all the different things that you could do to improve on the design. And, some of them, like IPC 7351B footprints, might seem pedantic to some people. But in a business, where you're taking your design and having an EMS build it, or, you've got other contractors involved, it actually does help in terms of being able to automatically detect whether the footprint is, can be used with automatic optical inspection, AOI, not AI, or AXI, right? Automatic X-ray inspection. So the footprints are kind of a necessary thing to get right, among many, many other things.
Is there anything that we haven't covered? Is there anything you'd like to add?
Yes.
Now's the time.
There are a lot of things to add, but no, I realize that we have a limited amount of time, and I appreciate your attention and your insight into knowing how important this kind of part of the printed circuit board design field that's emerging, is. So I do appreciate your insight. There's a lot more, yes, obviously, but we ask your audience to, they don't have to upload their own design if they're nervous about that, but they can use any of the example designs that are on the website and run it themselves. We do have confidentiality agreement on the website, which covers our, potential customers that are uploading sensitive designs, but there is some, there is some alternatives to that too. Your company might have a strict policy on its own CDA, and that's fine. There's a button you can click on the website to say, hey, we want you to look at our own company CDA and sign off on that before we upload a design, and that's fine. We can do that. And there's even a extra secure method of uploading your design. So there's obviously we use HTTPS and TLS 1.2, the normal, website kind of interface encryption, but you can pre-encrypt your design if you want. And using OpenSSL, you can pre-encrypt it and then put the design up onto Tomachie, and it will decrypt in memory only and process your design and then deliver the results in an encrypted format. So even if a human could get into our SOC2 data center and observe your design, they wouldn't have access to the file. So it's a way of adding another layer of protection, and we explain it in more detail on the website.
All right, CJ. Fascinating stuff. Best of luck.
Likewise. Thank you, Andy. Yeah, I appreciate you having me on. It was a lot of fun speaking with you.
Once again, I'm Andy Shaughnessy for PCB Chat. Thanks for listening.